Okay, looks like we can go ahead and get started. So I guess I'll start with question of the day. That was an interesting question that we had last time, suggested by one of our students, your favorite season. I'm actually one of those strange people who likes kind of drizzly, cloudy, whatever weather, so I think I'm probably one of the minority of people who like the winter better. But so that was an interesting question. I want to say a little bit about where we are and kind of what the plans are going forward. I've mentioned that there normally would be preparing for a midterm. You know, I don't want you to freak out that I've got a link here for midterm resources. I'll talk about that in a second. There isn't a midterm that you have to do, but I think that there's an educational benefit to you kind of pretending there was a midterm, you know, or preparing for it as if there were a midterm. I think that you want to try to have, as much as possible, the same kind of experience that students have during the regular quarter. And what I see students get out of preparing for the midterm is they're reflecting on the things that we've learned so far, and they're kind of trying to pull everything together and with some practice, you know, with exam questions and so forth. So I think it's a useful exercise. I think it'll be helpful to you when we get to the later homework assignments, particularly homework 6 and 7 are somewhat longer than what we've done before. Let me show you the calendar first. So in today's lecture, I'm going to be talking about what are known as assertions. This is a logic issue. It's a way of understanding code, and it's something that we include on the midterm. I think it would be good for you to practice some of these things, although it's not essential for a homework 5 that you're working on. So if you kind of want to finish up homework 5 first and then think about some of these other things, you know, that came from the midterm, do that later, that would work out fine, and you kind of got an extra week in there. So homework 5 is due on Tuesday next week, but there isn't a new homework that's going out next week. So that's going to give you some time after you finish homework 5 to kind of come back and reflect on some of these things that were part of the midterm experience for students in the regular quarters. So that's going to be today's lecture, that we're going to talk about that. Some things on Monday's lecture where I'm going to talk about logic more specifically and go over some midterm exam questions. And so again, it's kind of not really relevant to your homework 5, so that's good. You know, you could even kind of look at this lecture after you finish homework 5, kind of finish up that. So, and then this kind of is getting us to do that reflective part where we're thinking about the kinds of things that would have been on the midterm. I wasn't sure what to do with this middle lecture right here, and I decided that I'm going to cover an optional topic. So Wednesdays next week, it truly is optional. You know, it's if you're interested, then watch the lecture. And if not, you kind of have an opportunity to miss a lecture, and it's not going to be a problem. This is a different style of programming, something known as functional programming, which is very popular among a minority of computer programmers. Any of you who are mathematically inclined probably will enjoy this more than others. But it's a totally optional lecture. So if a lot of you decide not to watch that lecture, I think that's perfectly fine. If you want a bit of a break, you know, maybe you're even doing some of the other stuff I'm suggesting, kind of the midterm reflection and so forth, that would be fine. And then we're going to have 2 lectures that are on material from chapter 6. That's going to be Friday of next week and the Monday that comes after. That's going to be the material for homework 6, and I will give out homework 6 on this Monday. So it'll go out a little bit early, and then homework 7 will go out on this Monday. That's kind of all to deal with the fact that towards the end of the month we have a Monday holiday. So to kind of make things work out right, I'm going to be a little bit ahead of schedule, which is good anyway because you're not going to do a midterm. So you'll be glad to be a little bit ahead of schedule when we get to that material next week. But just so you know, the Wednesday lecture is completely optional. Okay. So other things that I've put on the class webpage is I did post midterm resources. So it does say here you don't have exams. Don't worry, you don't have to do exams. It does let you know how much time is allocated to students who do take the exams. And I've posted kind of my standard midterm resources. So I wanted to talk about this a little bit. I've posted a sample midterm. It's an old midterm that I gave before. And the cheat sheet is something that is part of the exam. So this is a page that's available to students while they're taking the exam. So you should kind of realize we don't expect people to necessarily memorize the names of all the string methods or the names of all the math methods, for example, and we remind people about if-else constructs. So the cheat sheet is something that would be part of the exam. The midterm, you can see these individual questions here. And there's a key. Now, my recommendation in terms of the key, I think that it is a mistake to look at the key early. I think it's better to try working on the problems yourself. In fact, I think it wouldn't be a bad idea to print out this sample midterm and give yourself 75 minutes and just kind of try to do the test and see how that goes. I'm going to talk about the kind of different kinds of questions down here in a minute. And there's a database of old exam questions. So we've been giving exams for many years. And so there's tons of kind of old questions. So this is a resource that's available to you that lets you look up old if-else simulation questions. There's tons and tons and tons of them. So lots of sample questions there if you wanted to have more things to practice. We don't give you answers to those sample questions. We could, but again, I don't think it's helpful to study answers. I think it's helpful to work on problems. So there's a whole bunch of sample exam questions there. And normally students would be spending, after they finished homework 5, they'd be spending a fair amount of time practicing exam questions to get ready for the test. You'll have to decide how much of that to do on your own, but I think that at least doing some of that is going to be helpful to get you in good shape for when we go forward with homework 6 and 7, and trying to make sure that you have an experience that's similar to students who've taken the course before. We don't know what's going to be happening in the fall, but many of you might choose to take 143 in the fall, and you're going to want to be in good shape relative to what other 142 students have done in the past. So, and I'm probably going to post a few more resources here. I'll talk about it again next week in Monday's lecture. We'll say a little bit about it. So let me say a little bit about the structure of the test. So one of the things that I do on the midterm is that since I assume that we have a fair number of students who are novices, I try to structure the test in such a way that novices can do well on the test. This first set of questions that I've highlighted here are questions that we refer to as mechanical style questions. So you don't have to write code, you just have to tell us what an output is, or we'll see the assertions questions where you're filling in certain blanks with different words. So you're trying to understand code is kind of what's going on with these different style of questions. And these questions add up to 61 points. That's a good chunk of points. So we do that on purpose because we want novices to know that they've got kind of a good base of a score, before they ever get to the programming questions. We don't want to kind of drown you in programming questions. And an interesting thing that we find is that people who have prior programming experience sometimes get lower scores on these mechanical style questions. And I think it's probably because they don't study them. They don't practice it. These mechanical style questions are things where anybody can learn to do these things. So that's one of the nice properties that they have. And when students actually take the test, I noticed that they don't really spend 61% of the time on these questions. The more you practice, the faster you get, and they tend to kind of go through these in a shorter period of time, which gives them more time to work on the other questions. So I do believe that all of these mechanical style questions are useful practice. They are helping to reinforce skills that are important skills to have. Psychologists have kind of told us that in order to be able to move to a higher level of comprehension, that you kind of have to train your brain to be able to do some things very automatically. And these mechanical style questions kind of reinforce those very basic skills that are going to make it easier, that when you go forward, you're not going to be having to struggle with these issues while you're dealing with newer ideas that you're going to be applying. So anyway, I think they're all helpful things. Practice really does help. I've seen this very much with students. Sometimes there are some people who seem to pick up programming more easily than others, but this is the case where it's truly the case that practice helps a lot. Then I do 2 15-point programming questions, which are, somewhat open-ended in terms of what I might ask. So no graphics, the graphics just didn't seem to fit on the exam, so we don't do that. But otherwise, it's testing things that we've done on other homework assignments. So for loops, while loops, and then testing certain patterns that we've talked to you about, like cumulative sum, fence post loops, sentinel loops, max-min computations, counting tasks, dealing with combinations of ints and doubles, having methods that have parameters and that return things. So kind of all of the stuff that we've been doing in our homework assignments, I include some combination of them in these 2 15-point questions. So they're good questions to practice. They're kind of helping to reinforce the basic programming skills that we hope you've developed in doing the homework assignments up until now. I always include an extra problem at the end as a way of kind of distinguishing at the high end, kind of A's versus B's, for example. The question that I tend to ask, this kind of hard question that I ask on the exam, it probably should be worth something like 25 points in terms of how hard it is relative to some of the other questions. But if I made it worth 25 points, then it's kind of like everybody who doesn't get the hard question is suddenly has a max score of 75. So I purposely make this worth a relatively low score relative to how hard it is, but I warn people about this, that don't waste your time on the hard question if you don't have solid answers to the other questions. There's always some partial credit, even on the hard question, like getting the method header right or getting some basic elements of the solution. But there's usually some core idea to solving the hard question, and sometimes only maybe a third of the class will figure out that hard idea, and the other 2/3 won't. So the other 2/3 aren't going to tend to get a high score on this question, but they often get partial credit of maybe 3 points out of 9 or something. So this leads to some level of distinction at that very high end. But so if you do a sample test and you go through this, then don't spend too much time on this, and don't worry about it if you're among the 2/3 who don't get this question. It doesn't mean that you're failing the course or something like that. The far more important things are the mechanical questions and the 2 15-point questions. Those are the better ones that are practicing what we've learned and are kind of a gauge of where you're at in terms of mastering the material. Hard question, some people see it, some people don't. It's not that big a deal. So anyway, that's kind of the structure of the test. I assume that students are going to kind of look at this sample test, and then maybe it doesn't make so much sense. I mean, some people may not give themselves the 75-minute, limited time to do the test. What I'm going to do is I am going to post a second sample midterm. I don't normally do that, but sometime next week I'll post a second sample midterm in case you want to be reviewing these materials to prepare and you want an extra opportunity to try to give yourself a test. So anyway, there are lots of resources here. You're not necessarily going to use them all. Each of you will kind of decide for yourself what you want to do. And we're still trying to figure out exactly what we're going to do in section next week, because we kind of have an opportunity there to do something different than what we've normally done. Okay, that's probably enough of me commenting on what would have been on the exam, and so what I hope you're going to be studying once you have finished homework 5. So let me get to talking about this material that has to do with what we call assertions. So I usually begin this, I'm going to just kind of give those special comment characters here that let me I'm just going to type some text here. It just gives me a little way to be able to type some things as I talk about it. I usually start with a question here, which is that a lot of computer science programs are housed in colleges of engineering. That's true here at the University of Washington. And one of the things that I've learned in dealing with faculty from engineering schools is that, particularly the old curmudgeons, but lots of people in engineering colleges, they just love physics, and there's kind of, why do they love physics? Why is physics such a big deal for them? I can tell you a true story. I was at Stanford in the 1980s when we were designing an undergraduate major. Stanford didn't have one at first, so we were designing a computer science major in the late 80s, and we presented it to the engineering college because we were in the college. I had just recently moved into the college, actually. And one of the comments, that was a pretty funny comment, someone pointed out, look, if we accept this program, you are going to be the only major in the College of Engineering that has science in its name, and you are requiring less science than all of the rest of us. How can it be that a computer science major is requiring less science than all the other engineering degrees? So that was a fair question, it's kind of this issue of why do they love physics so much? Are they just, old fogies who don't know, what's important or what's not important? Maybe they're wrong. So I usually ask the class, and I usually get some pretty good answers to this. And sometimes I'll get a funny answer to it, So basically, here's the thing. Engineers design things that are going to be built in the physical world. So like an engineer might design a bridge. So if you're going to design a bridge and you want that bridge not to collapse, then you're going to want to understand things like gravity. If there was an engineer who said, that gravity stuff was too hard or whatever, I don't care about that gravity stuff, I'll just build my bridge ignoring the concepts of gravity, that's a bridge I would not want to drive over, or at least until many other people had driven over that bridge to convince me that it was safe. So engineers study physics because they build artifacts in the physical world, so they need to understand the scientific principles of the physical world so that they will build artifacts that work, that operate well in the physical world. Well, so what is it that we're doing in computer science? Here at UW we call it CSE, Computer Science and Engineering. Well, sometimes, some of us build physical artifacts. Some of us have ties to electrical engineers and are doing things that involve sensors and other kinds of physical devices. But a lot of us are doing software. And what's software? Software, programs are artifacts that we build, but they don't exist in the physical world. They exist in a virtual world. And so what's the physics of the virtual world? What are kind of the principles that dominate the physical world? And what I would say is that math and logic is the corresponding set of things that tell you about the limits of the virtual world. It tells you, for example, limits on how fast your program might run. It's like it's a kind of gravity. There may be limits to, how well this thing is going to actually behave. And if you have programs that have logic errors in them, that have bugs in them, it's going to be like a bridge that collapses. So you're going to need to understand logic as a way of knowing how to build programs that are logically sound. So math and logic are to computer science what physics is to many of these other engineering disciplines. In fact, the person who was chair at the time that we were doing this proposal back at Stanford, a fellow named Jeff Ullman, famous computer scientist, Ullman made an interesting point, which is that he said that if you take a look at the math plus science units that are required of the various majors, you add the two together, how many units of math, how many units of science, that actually the proposed computer science major had a higher requirement than any other major in the College of Engineering. So when you added in math with the science, we actually were requiring more, not less, than what other people were requiring. So, I mean, that's all meant to say math is important, logic is important, what we're studying, well, what this assertions thing it helps us study, what I'm going to talk about in Monday's lecture, what we're kind of reflecting on before we move forward. It's all very important to programming. And it kind of also helps you to be able to do good debugging. There was a session yesterday for the engagement activities. Some of the TAs might be talking about debugging in section next week. We're still, as I said, kind of figuring that out. In the early days of this, there used to be a field called program verification, very popular and kind of it became popular in the 1980s. And the idea that you would prove programs correct, almost like a mathematical proof, that you would prove that your programs are correct. Actually, Don Knuth, this other famous computer scientist that I've talked about, made fun of that idea. He had some famous quote that, I don't have confidence that this program works, I have only proven it correct. He was kind of making the joke that, well, your proof could have an error in it. So I think, early on program verification, people at first thought it sounded like a great idea, and then maybe it wasn't so great after all. It's a hard thing to do, but it didn't go away. The people working on this are very interested in it, and it's been far more successful, I would say, in recent years, and there's been more interest in recent years. So kind of the name that's given to this kind of reasoning these days is formal methods. Google it, and you'll find that you'll find a Wikipedia page about formal methods, a kind of a description of computer scientists who are trying to apply mathematical and logical reasoning to programs. I mean, some of the kinds of reasons that we'd be interested in this is security issues. So you'd like to be able to make certain security assurances about your code, that you want to know that it's not vulnerable to attack by hackers. And so formal methods has gotten a lot more interest because of things like cyber terrorism or even just hacker attacks. So in any event, formal methods is very interesting. That's kind of the computer science field that deals with the kinds of things we're going to do. So I mean, in a way, you could think of it as we're doing a little bit of formal methods. We're doing some examples here that help us to understand a little bit of what they think about in that field, the kind of reasoning that they use. So I've got a little bit of starter code here where, I'd set up a scanner, read in an n, and I kind of am posing the question here in a comment, is n greater than or equal to 0 at that point in program execution? Well, what do you know about n? You know that you paused, the console scanner, you asked the user, for a number, you type something in, is it greater than or equal to 0? Maybe, maybe not. What if you said, n, please make it greater than or equal to 0? What if you pleaded with the user to give you something greater than or equal to 0? Then would you know that it's greater than or equal to 0? No. Only if you get to assume that the user is giving you legal input. Now, we tell you on your homeworks that you get to assume that the user is giving you legal input. So we make it easier for you because it is hard to deal with situations where the user might not give you legal input. But, in general, just asking the user is just not going to do it. It's not going to guarantee that this thing is greater than or equal to 0. So what you're going to see, this is what we would call an assertion. It's a claim. It's something that's testable. Is it true that n is greater than or equal to 0? And it might be true, and it might be false. So the kinds of questions that the assertions questions that we do, there are kind of three possibilities that we consider. It could be that this assertion, this claim, is always true at that point in program execution. It could be that it's never true at that point in program execution, or it could be the in-between, where sometimes it's true and sometimes it's false. And the right way of thinking about the sometimes, so especially if you talk to any of the other students in the class about this, or your TA, or if you do one of these in section next week, if you're trying to think about this, if someone kind of tells you that it's a sometimes, then they should be able to give you a value of n when it's true, and a value of n when it's false. So they should be able to give you one of each. So here I guess I would say, well, if the user typed in 18, well, that's greater than or equal to 0. If the user typed in -8, that's not greater than or equal to 0. So we would kind of say this is sometimes. It's sometimes true, sometimes false. We don't know very much at that point. Well, but think about, what if I had an if? What if I said if n is greater than or equal to 0, and then if I asked is n greater than or equal to 0 here, and I have some code that I execute. What about that? Well, how does the if behave? You know, Marty Stepp in the slides had that little railroad diagram that shows you that it performs the test, and it only goes to the body of the if the test evaluated to true. So what you would know in this case is that this is always true at that point in program execution. N it's got to be greater than or equal to 0, or you wouldn't have gone into the if. That's how the if works. What about asking afterwards, n greater than or equal to 0 here? Well, it kind of depends, but in general, the if doesn't give you any kind of guarantee about what would be true after the if is done executing. So we would say that most of the time, it's sometimes. Most of the time we don't know. Most of the time it could be one or it could be the other. So that's kind of how the if behaves. Let me make a copy of this and let me make and paste it in so that I can talk about the if else. So that's kind of another construct we've seen, right? So what if I had else and I wanted to know is n greater than or equal to 0 here, and then there was going to be some lines of code. So what if it was an if else instead of being a simple if? Well, we know, again, the slides showed you the railroad diagram. We know what an if else does. An if else branches in the two directions. You either go this way or you go this way, depending upon how the test evaluates. So if n was greater than or equal to 0, we would always end up in this branch. And if it wasn't greater than or equal to 0, we'd end up in the else. So this would be never true. It would never be true in the else branch. Otherwise, you couldn't have ended up in the else branch. That's the whole point. You end up in the else branch when it's not true. So n greater than or equal to 0 is never true kind of at the top of this else branch. So these are all situations where we can kind of use the properties of constructs like an if or like an if else to help us figure out various things. And kind of afterwards, we'd have a similar answer to what we had before. Now let's think about the while loop. So what if you had while n is greater than or equal to 0, and you were going to ask, is n greater than or equal to 0 here? Some lines of code. And then we're going to ask afterwards, is n greater than or equal to 0 here? So let's kind of do the same reasoning about this one. So the while loop is like the if, in that, it performs the test, and if the test evaluates to true, then it enters the loop. So if you're here, it would always be true that n is greater than or equal to 0. That would always be true if we've entered the while loop. What about here? This one's an interesting case. So what about after the loop? Now there's some tricky situations. You can have a case where you're in an infinite loop. So maybe you never make it to here. You kind of get stuck in the while loop. And we don't want you to worry about infinite loops when you're reasoning about these possibilities. We want you to think about the cases where it wasn't an infinite loop. So if it ever does get to here, what would be true? And we know that the while loop, you're kind of trapped in that while loop, while n is greater than or equal to 0. It keeps performing the test over and over and over and over again. And as long as n is greater than or equal to 0, it's going to stay in the loop. So if it broke out of the loop, it must be because this is no longer true. So this would never be true after the while loop. N greater than or equal to 0 would never be true after the while loop. Now again, you might not get there because of an infinite loop, but if you do get there, it's because n is no longer greater than or equal to 0. So that's a lot of the kind of reasoning we do in these assertion style questions, if, else, and while. There's a different kind of reasoning, and we have you do some of this, but not too much because it gets a little bit tricky. But sometimes you have to reason about what exactly code is doing. So what if I said if n is less than 0, I'm going to say n is assigned to minus n. And then I asked, is n greater than or equal to 0 here? Now, I said earlier that after an if, you don't tend to know. You know that it's normally sometimes. But think about what this one does. If n is a negative number, it's turning it into its negation. So if n was a -3, for example, then setting n to minus n turns it into a +3. So what I claim is that n greater than or equal to 0 is always true here. And I could give you an example. If n had been 8, it would still be 8. And so I've given you an example where it's greater than or equal to 0. And if any of you think that it's sometimes, you've got to give me an n. You've got to come up with an n where this would not be true. And you're going to find there isn't one. There isn't an n you can come up with that would make this not true. And that's why it's always true. That's why that's kind of the right answer here. So those are examples of the kind of reasoning we want you to be able to do. It's all included in the chapter. Some of this is in the slides as well. So there's a kind of a nice review of this. And I want us to work on a couple of examples. Now, let me mention that during the normal quarter, what I'd be doing at this point is I'd be telling the TAs to pass out this handout. So I have a handout here, handout number 7, that has a sample assertions question. It shows some code with various points identified and a table for you to fill out. And filling out the table, you either fill it out with always, never, or sometimes. Kind of put that in the different things here inside of the table. There's a first assertions question here. There's a second assertions question. So normally I would be getting you to do that. Obviously I can't do that because we don't have the ability to pass out a handout. What I've done instead is that on the class webpage, I've put a link to the handout for the assertions lecture. So if you go here, this is that thing I was just showing you. That's the first page. That's the second page with a second problem. There is a third page with a key, although I would recommend not looking at that yet. That I think it's, as I said, it's better not to study answers. It's better to kind of study the problems. But I would say that if you have a printer easily available to you, I would print that handout right now. I think it's helpful. I think it's a little easier to keep it clear, to be able to have the code separate from the table, and you might want to write some notes. So if it's easy to do, then I would say pause this right now, print that handout as we go through some of these examples. Okay, so let me start with the first assertions question, and it kind of shows you this code right here that has identified various points of interest. And then there's a table to fill out. So I've made a kind of a crude version of that table here in comment form, where we're supposed to be thinking about these 3 different tests and the different points in execution. This is just my own version of this little table right here. So I think it's easier if you had the printed handout, but even if you don't have the printed handout, I think you'll be okay to be able to follow along. All right, well, let's talk about these. Let's do a couple of these. So let's think about point A. So where are you at point A? What's going on? You called a mystery method, passing in an x and a y, and you've set z to 0. So at point A, what do we know about x being less than y? Could it be less than y? Well, sure, they're parameters. I could have given you 2 and 8, where x is less than y. Does it have to be less than y? No, I could have given you 8 and 2, where x is not less than y. So this would be something that's sometimes true, sometimes false. How about x being equal to y? Oh, well, I could have given you 8 and 8. So again, whenever you're answering a question like this, trying to justify an answer, you should be coming up with scenarios. Here are values of x and y for which it's true. Here are values of x and y for which it's false. And so I've given you some where x and y aren't equal. But they could have been 8 and 8. So this is a sometimes. I've got a scenario where it's true, a scenario where it's false. And how about z being 0? Now, z is different. Z is a local variable that we initialize to 0. So it's not coming in from outside with a parameter. So you don't have kind of the same flexibility that you would have in the parameter case. And so this is something that's always true, because we set it to 0 and nothing has changed about z here, so that would always be true. How about this, point B, just inside the while loop? Well, this involves some of that reasoning that I mentioned, back here when I talked about the while loop, that you'd know that kind of that test is always true inside of the while loop. So we would know that if you're here, it must be because x is greater than or equal to y. Well, x less than y, how does that relate to x greater than or equal to y? Those are negations of each other. The negation of x being greater than or equal to y is that x is strictly less than y. So since it would always be true that x is greater than or equal to y at point B, so it would never be true that x is less than y at point B. X being equal to y, I've given you different scenarios. We've got to have a scenario that enters the loop. So an x that's greater than or equal to y, well, what if the x had been 8 and the y had been 2? Then we would have entered the loop with x and y not being equal. What if they had been 8 and 8? Then and then 8 would be greater than or equal to 8. We would have entered the loop with x and y being equal. So I've given you a scenario one way where they're not equal. I've given you a scenario another way where they are. And in both scenarios, we would have entered the loop. So this is a sometimes. Z being 0, I'm going to kind of put a question mark here for right now, because you might think to yourself, well, where was I just before point B? So this is kind of reasoning you want to be able to do here. By the way, I didn't mention this before, but let me mention that what I find is that people who are kind of very quick to pick up programming, and people who've done a lot of programming, so like people with prior programming experience, they've practiced it enough that they tend to think this way automatically. So I think one of the values of doing an exercise like this is that those of you who don't have as much experience or who don't pick up programming quite as quickly, this is kind of getting you to think in this very important way, that others, are kind of used to doing. So where would you have been just before point B? Well, you might have been at point A, where z was 0, but you might also have been at point D. You might have come back around the loop, because you can go around and around the while loop. So I'm not going to fill this one in yet. I'm going to kind of wait until we've thought about point D. So, let me also mention that at point C, kind of between B and C, nothing has changed about Z. So whatever's true at point B would also be true at point C. So there's something, we'll fill that in a minute, but whatever was true here would still be true here because Z is unchanged. What I usually recommend at this point to people is I want you to think about point C and point D. So I want you to think about kind of these next two rows and fill in the 2 blanks here other than this one and the 3 blanks here for point D. So I normally put up a timer and I give people a minute to work on this. You're watching a video, so you have the ability to pause. And I think it would be worth your while to pause the video for a minute, come up with your answer, and then we'll then continue, and we'll talk about the answer. So my recommendation, pause. Figure it out. I'm not going to do the actual pause because some of you may not need quite as long for a pause. So, all right, so I assume you've thought it through, you have your own answer. Let's talk about it. What's going on here after point B? We're taking x and we're resetting it to be x minus y. So, and we want to think about things like x being less than y. So we knew that x was never less than y at point B, when we entered the loop. It couldn't have been true that x is less than y. But could it be less than y now? So is it possible that when we subtracted y from x, now x is less than y? The answer is yes. So you think of a scenario. So what would be a scenario? I'm thinking of one. If x had been 3 and y had been 2, then we would have entered the loop because 3 is greater than or equal to 2. So it would have been a greater than situation here. But then when we subtract the 2 from x, x becomes 1. And now 1 is less than 2. So that's a scenario where x has become less than y. Does it have to be less than y? No, I mean, x might have been 8. It was an example I was giving before. X is 8 and y is 2. And if you subtract the 2 from the 8, it becomes 6. It's still greater than the 2. So this is something that's sometimes true, sometimes false. How about being equal, x being equal to y? Well, we had seen, when we subtract x from y, so it has to be an x that's greater than or equal to y. So what if we had a situation where it had been x was 4 and y was 2? So if x was 4 and y was 2, we'd subtract 2 from the 4, and now we'd have 2, 2. So now they would have become equal. So it could be that after the subtraction, I mean, I've given you a scenario where x becomes equal to y, but it's not always the case. We had some other examples like 8 and 2, where, x ends up being 6, which is not equal to the y. So this is also sometimes true, sometimes false, is what we put here. At point D, we're not changing anything at point D that has to do with x and y. We're only changing z. So that means that whatever was true at point C would also be true here. Whatever was true of x and y at point C would also be true at point D. So we just kind of carry down the sometimes. And what about z being 0? Well, what we did is we incremented z here. So z went up, and then we got to point D. Z had started out at 0, so that means that it would now be 1, if we got to point D. And what if we get here again later, we'd come back around the loop, and then z would be incremented to 2. And if we went around the loop again, z would be incremented to 3. If we went around the loop again, it would be incremented to be 4. So, z just goes up and up and up. It can never come back down again. It can never get back to 0. So at point D, it is never the case that z is 0. Never. Because it's going to be at least 1. Okay, so this lets us answer what was true at point B. So at point B, if we had been at point A, we could be entering the loop with z being 0, but if we're coming around the loop, then z is 1 or 2 or 3 or something else. So we have scenarios where z is 0 and scenarios where it's not. So this becomes sometimes true, sometimes false. Point E, I'd kind of recommend again, pause. Think about what you think the answers are. Okay, let me talk about it, assuming that you've thought it through. So after the while loop, I had mentioned this idea before, that after the while loop, we know that that test is never true. So x greater than or equal to y is never true at point E. Remember that x less than y was the negation. That's the opposite. And so if the greater than or equal to y is never true, then that means that this is always true. That it would always be the case that x is less than y. And if it's always less than y, then it can't be equal to y. So that would be never. Now, you might think that if we were at point E, that we had just been at point D. So you might think that the answer here is never, because you might say, well, I was at point D just before. But think about it. Is there a scenario where you weren't at point D just before? Where else might you have been besides point D? And the other place you might have been is point A. Maybe you never entered the loop. Well, how would that happen? Well, what if the x that was passed in wasn't greater than or equal to y? What if it had been something like a 2 for x and an 8 for y, so that x was already less than or equal to y? We never went into the loop, and we get here with z being 0. So the right answer there is sometimes. There's a scenario each way. Sometimes it's 0, sometimes not. Okay, that's that problem. Let me look at the second problem. It's on the second page of the handout, back page, if you did double-sided copying. This one is computing an exponentiation, x to the y power. It's using what's known as a precondition. So this is something that was described in chapter 4. So there are certain methods that have kind of caveats associated with them. I mean, like a classic one I'm sure you'd think of is the square root, math.square root. You can't ask for the square root of a negative number. So we call that a precondition, something that has to be true before you're allowed to use a method. So it'd have to be true that the number you're asking for the square root of is greater than or equal to 0. And we're saying the same kind of thing here too, that y has to be greater than or equal to 0. So at point A, what would we know? We'd be passed a y. Now I want you to assume the precondition is true. So we will assume that y is greater than or equal to 0. So could it be 0? Sure, they could have passed in a 0. Does it have to be 0? No, they could have passed in 8. So this is sometimes true, sometimes false. How about y mod 2 being 0? What is that testing? Stuart loves mod. We've seen this before. Even numbers. Is y an even number? Well, sure, I could have given you 8 for y. Does it have to be even? No, I could have given you 7. So this is sometimes true, sometimes false. Point B is inside the while loop, so we entered the while loop. So that means we would have guaranteed that y was greater than 0. So could it be equal to 0? No, that would never be true. Even, sure, sometimes yes, sometimes no, because, like those 8 and 7 are different values of y that would have gotten me into the loop, but one is even, one is odd. Well, I want you to notice that the next thing that happens is that we have an if-else that goes to either point C or point E, and y is not changed. We don't do anything to change the value of y, we just do the testing. But that does give us information. And so I want you to, you could remember what we had said about what was going on when you had an if-else. There was kind of that before. So I want you to pause and think about what's true at point C and at point E. I want you to do those two, not D and F, but C and E. So think about what's true at point C and what's true at point E. Pause, think it through. Okay, we'll get back together. The point is that here we're testing to see whether y is an even number. So if we went into the if part, y was not changed, so it's still never a 0. But do we know that it's an even number? Yes, we know that it's always an even number if we went into the if branch. If we went into the else branch, again, y couldn't have changed. If it was never 0 at point B, it's still never 0. But this would never be true. So we branch. We either go to the branch for evens or we go to the branch for odds, one way or the other. Well, now I kind of want you to think about what's true at point D and what's true at point F. This one is one of the most useful ones for you to think about because not really obvious at all. So this is a really good one to pause and think it through. So I'm assuming you do a little pause. So let's talk about it. What's true at point D? All right, well, at C, we knew that we had an even number. And what have we done to y? We've divided it by 2. Is there an even number that when you divide it by 2, it gives you a 0? Can you think of any even number that when you divide it by 2, it gives you 0? And the answer is no. There's no such even number. And so it's still true that y is never 0. How about whether y is even after we divide it by 2? Is there an even number that when you divide it by 2, it's still even? Sure. How about 8? Then it becomes 4. Is there an even number that when you divide it by 2, it becomes no longer even? Sure. 10. You divide it by 2, it becomes 5. So this is something that's sometimes true, sometimes false. Point F is an interesting one. We knew that y was guaranteed to be an odd number. And we subtract 1 from y. Is there an odd number such that when you subtract 1 from it, you get 0? The answer is yes, and that number is 1. So there is an odd number that could produce a 0, but it doesn't, not all odd numbers produce a 0. It could have been a 5, in which case you subtract 1, you get a 4. So this is sometimes true and sometimes false. How about y being even? This one is probably the trickiest of them all. It's an odd number, and you've subtracted 1 from it. So like if you had a 9, you subtracted 1, it's become 8. That's a case where it's become even. It went from being odd to being even. Can you think of an odd number such that when you subtract 1 from it, it gives you an odd number? I challenge you to come up with such an odd number. There's no such number. So basically, this is always true. You always get an even number when you subtract 1 from an odd number. G kind of combines those two. You could pause if you wanted to, but maybe you're getting tired of pausing. But I can let you know that you kind of reason about what's true at D and reason about what's true at F, because the branching comes back together again. And there's so many different possibilities here that we end up with sometimes. You could, again, pause if you wanted to, but maybe by now you're tired of pausing to think about H. So what we would know after at h is that y greater than 0 is no longer true. Now that doesn't necessarily mean that y is equal to 0 unless you take into account the precondition. And I did want you to take into account the precondition that we're not thinking of negative values of y. So if y wasn't negative and we know that it's no longer greater than 0, then the only possibility is that it's become equal to 0. And is 0 an even number? Yes. So that's the answer that I would give there. It does rely on the precondition, and I won't normally make you have to reason about the precondition. So this is something that does exponentiation. If you're interested, you could think a little bit about what this one does. I'll mention at the beginning of next lecture what it is that this thing is computing, in case you're interested. The key is page 3 of that handout. All right, well, that's what I had for today, so we can go ahead and wrap up.